So let's look at the steps that are involved in drawing covalent compounds. The first thing you have to do is determine the total number of valence electrons for all of the atoms in the formula. Now remember, there's a difference between covalent and ionic compounds. Covalent compounds don't have metals to give them the extra electrons that they need to satisfy the octet rule. As a result, they're going to pool all of their electrons together and then kind of divide them up so that everybody has the octet. The second thing that you have to do is you're going to choose a central atom. You're going to kind of go with your gut here. Over time, as you practice, you'll learn which ones are most likely to be the central atom and which ones are least likely. But just to give you a quick rule, whenever you have carbon, that should be your central atom. Hydrogen never should be your central atom. Number 3, connect all of the other atoms to the central one with single bonds. Now a single bond represents 2 electrons, so this is going to be 2 from the total number. And you are going to keep counting all of the electrons that you use to connect everything and subtract that from the grand total number of valence electrons. Eventually this grand total number will go down to 0. And if you get it down to 0 and everybody has the octet, then you did it right. The next thing you're going to do once all of the other atoms are bonded to the central one with single bonds is you're going to give everybody else an octet. And that means everybody else needs 8 unless you're hydrogen and you only need 2. So you're going to add all the remaining electrons to the outer guys first, give them all an octet, then you put any extras around the central atom. And then if you fall short, you're going to have to rearrange some unshared pairs of electrons. And we'll go through each of these steps one at a time until you get the hang of this. So first, count up total number of valence electrons, create a pool or a bank of electrons that they can all divvy up and use. You're going to figure out which one's your central atom. You're going to connect all the other atoms to the central one with single bonds. You're going to give all the outer guys an octet. Anything left over goes on the central atom. And then you're going to do some rearranging to make sure that everybody has an octet, including the central atom, because sometimes that doesn't have one, everybody else does, and you ran out of electrons to use. So let's go practice. Now imagine I have NH3. Nitrogen says, I have 5 valence electrons, I need 3 more, but there's no metals to give me some. And little hydrogens are sitting there with 1 each. So there's 3 hydrogens based on the formula, so 1, 2, and 3. They each have 1, they need 2 to satisfy the octet rule, and there's no metals there that are willing to donate electrons. So as a result, they pool their electrons together and have 8 electrons. Now it's really a good idea to keep track of your electrons down the side. When you hit 0, you know that you ran out of electrons, you may or may not be done. And depending on who has an octet and who doesn't at this point, you may have to do some more steps. But we're going to start off with some easy ones. So we're going to pick our central atom. Now I told you before it's never hydrogen, so start with nitrogen. And then you're going to put your 3 hydrogens around your central atom. And you're going to connect them all with single bonds. Now single bonds represent 2 electrons each. So far, from my bank of 8, I've used 6. There's 2, 2, 2, that's 6, so 8 minus 6 leaves me with 2 more. Now all of my outer guys have an octet. They technically don't have 8, but they're satisfied. They have their 2, because remember hydrogens can only hold 2 electrons in their first energy level. But my nitrogen's not happy. Nitrogen has 2, 4, 6, it needs 2 more, and what luck, we have 2 in our bank. So we're going to grab 2 and draw them as unshared pairs of electrons. These are unshared. They're just going to hang kind of around the nitrogen for now. Meanwhile, the hydrogens are going to share 2 electrons each with the nitrogen. So all in all, the hydrogens are all happy. The nitrogens have 2, 4, 6, 8, so nitrogen's good, and everybody's all set. So we're done, and that is what our covalent structure looks like on paper. It's not necessarily what it looks like in 3D. If you were to look at this in 3 dimensions, you would first look at your nitrogen in the middle, add your 3 hydrogens. So far it looks like trigonal planar, because it's 3, looks like a triangle, and they're all on the same plane. However, you have to add that last set of electrons. Remember the unshared pairs of electrons that were at the top? That's what our structure looks like in 3D. And this kind of looks like a pyramid, so this is trigonal pyramidal. So here we are with carbon and fluorine. They don't have a metal to give them the electrons they need. Carbon comes in with 4 electrons, fluorine has 7 each, and they're each short of the octet. So they look at each other and say, let's pool all of our electrons together. There's only one carbon, so carbon's got 4. There's 4 fluorines, so 4 times 7 is 28. And then when you add carbons plus fluorines together, we get 32 electrons. Now you shouldn't be thinking about ownership anymore. Remember, these guys are going to work together, they're going to cooperate, covalent bonds, they're going to cooperate and share their electrons. So we have 32 electrons to divide up and give everybody an octet, make everybody happy. Now, I told you before, you should always start with carbon. Carbon should go in your center, never hydrogen. And these fluorines, these halogens, usually can only make one bond, so they're not really good center atoms. So the formula is CF4. So I put my C in the center and my 4 F's all around it. And then the next rule is to connect all of those guys with a single bond. Now remember, a single bond represents 2 electrons. So if we tally up the electrons, we've got 2, 2, 2, and 2, 2, 4, 6, 8. So 32 minus 8 leaves us with 24 electrons. Now the next rule is give all the outer guys an octet. So I'm going to use the electrons in my bank to give everybody 8 electrons. So 2, 4, 6, plus a 2 in the bond, that fluorine's happy. This fluorine has 2, 4, 6 in the electron cloud, plus 2 more in the bond, so that's a grand total of 8 in that cloud. 2, 4, 6 plus 2 in the bond, so that's 8. And this fluorine, you can imagine, probably needs 6 plus the 2 in the bond. And that one's got 8. Now let's look at how many electrons we put down. 6 plus 6 is 12, plus 6 is 18, plus 6 is 24. So I just emptied out my bank of electrons, and I'm down to 0. Now you should always check to make sure you hit 0, because if there's extra electrons, you did something wrong. Now let's take a look at what shape this is, because on paper, it looks like these angles are really 90 degrees apart. And that's not what it's like in real life. So here's our central atom. Here's our carbon. Fluorine, 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 fluorine. There's our 4 fluorines. Now there were no extra unshared electrons on that central atom. Everybody was happy. And this is what our shape looks like. In the real world, they're not 90 degrees apart, but actually 109.5 degrees apart. They're all equidistant from each other. And this is what we call a tetrahedral shape. So now we just did CF4. Now that wasn't in your notes, but why don't you give CCl4 a shot? Why don't you pause it now and go through the same steps that we just did with the CF4 and try it for this model. All right, hopefully you've given this a shot. Now let's go through it together here. The first thing you do is always count how many valence electrons each element is going to contribute to the pool. So carbon's going to give up 4, because that's all it has, and chlorine's in group 7, so it's got 7, and there's 4 of them, so all the chlorines together pool their electrons, and they've got 28. So 4 plus 28 is 32 electrons. Then the first thing you do when you're ready to start building is grab your center atom. Now it's going to be carbon here. Carbon's always a good center atom. And then your chlorines go all around, and you connect them with single bonds. Now single bonds represent 2 electrons each. So before you go any further, what do you think you should do right now with your pool of electrons? If you're thinking subtract 2 plus 2 plus 2 plus 2, if you're thinking subtract 8, then good. If you weren't thinking that, then you need to make a mental note and start thinking that. Every time you draw those bonds, that counts for 2, and that has to come out of your pool. If you don't keep track of your electrons, you will not know what to do at the end. All right, so the next rule is give all the outer guys an octet. So we're going to start with this chlorine here. Now this chlorine's got 2 in the bond, but it needs 6 more to get a grand total of 8. Remember, everybody needs 8, but what element? Hydrogen. Hydrogen only needs 2. So you should just be drawing 1 bond if you're ever drawing a hydrogen. Never, ever put dots around hydrogen. So what I'm doing here as I'm talking is I'm moving these electrons down so every single chlorine has an octet. And I'm keeping track of my electrons mentally, but let's do it on paper right now so we can make sure that we don't have any left over at the end. We put 6 more here, so 6 came out of the pool. 24 minus 6 is 18. We put another 6 here. 18 minus 6 is 12. We put another 6 here. 12 minus 6 is 6. And we put another 6 here. 6 minus 6 is 0. So we have no electrons left. Now this may or may not be a good thing. What you need to do is check your center element and see if the center element has an octet. If it does have an octet, then great, you're all done, as long as this is 0. If it doesn't have an octet, then we need to do stuff. But in this case, it's already got 2, 4, 6, 8. It's all set. It's happy. This is at 0. All the outer guys are happy. So our model is all done. Now we just have to think about what shape it is. You've got 1, 2, 3, 4 atoms bonded to the center. 4 is going to be, check your reference sheet, tetrahedral. So when you think about what this looks like in real life, there's going to be an atom going up. Here's your center atom. One kind of going out this way, one coming right at you. I know it's hard to draw on paper here, but one is coming at you out of the screen, and then one's kind of going back this way. So they're going in all 4 directions, and that's tetrahedral. All right, so let's try NBr3, and let's see what happens when we end up with extra electrons in our pool after we've given the outer guys an octet. So again, the first thing you do is always look at the elements involved and figure out how many electrons they're going to donate to the pool. Nitrogen's in group 5, so it donates 5. Bromine is in group 7, so it donates 7, but there's 3 of them, so 7 times 3 is 21. 5 plus a 21 is 26 electrons. So that's what we have to work with, exactly 26 electrons, and these guys are going to divide them all up so everybody's happy. Now pick your center atom. It's going to be nitrogen since there's only 1 of them. Bromines are going to go all around. You look at the formula to decide how many bromines. So there's 3 in the formula, so we put 3 all around. And then we connect them all with single bonds. Now remember, each bond is how many electrons? 2. 2, 2, and 2. What should you do before you move on? Subtract 6. 2, 4, 6. Subtract 6 from your grand total. Now all we have are 20 electrons left. And we're going to use those 20 to make all of these outer guys happy. Now remember, they each have 2, so they need 6 more. Everybody's got to get 6 from the pool, so they have a grand total of 8, because you count those 2 plus a 6 is 8. So there's 6 there, here's 6 here, and here's 6 more down here. 6 plus 6 plus 6 is 18. Oops. So we look at our pool and we say, well, 20 minus 18 still leaves us with 2. We have 2 electrons left in our pool, so what should we do with them? Well, all our outer guys are happy, but our nitrogen's not. The nitrogen says, I'm sharing 2, 4, 6 electrons with all you guys, but I need 8 total, so I need 2 more. So nitrogen says, are there any left in the pool for me? And the answer is yeah. There's a set, there's 2, so they go right there. And that cancels out the last 2, and our pool is empty. So just do a quick peek. This guy's got 8, 2, 4, 6, and 2 in the bond. This guy's got 8, 2, 4, 6, 2 in the bond. This guy's got 8, 2, 4, 6, plus 2 in the bond. And nitrogen's got 2 right here, 4, 6, 8. So everybody's happy, and our pool is empty. Now we have to figure out what shape this is. What you should look for are how many atoms are bonded to the central atom. So we've got 1, 2, 3 atoms bonded to the center. Now if you look in your notes, or if you look on the reference sheet, you've got 2 options for 3 atoms when they're bonded to the center guy. This one, 1, 2, 3, or there's your center guy, 1, 2, 3. So the question is, which one is it? Now the big difference between the two, other than shape, is the presence of these electrons. If there are electrons on that center atom, and there are, then it's going to sit up like a pyramid. If they're not there, then these 3 areas are going to spread out evenly. And remember, they're going to be 120 degrees apart from each other. But these electrons
cause it to bend down like a pyramid. So these outer atoms are all going to go down. And the little nitrogen is going to pop up and sit up like it was at the top of the pyramid. So let's try SO2. Remember the first thing, look at your formula, figure out how many electrons are all going to contribute. Sulfur's in group 6, contributes 6. Oxygen's also in group 6, and it contributes 6, and there's 2 of them, so 6 times 2 is 12. 6 plus 12 is 18 electrons. So these guys have decided, let's pool 18 valence electrons, and let's make this work. Let's split them all up so we're all happy. Now, pick your center atom. There's only one sulfur, 2 oxygens, so you could probably envision sulfur being in the middle and oxygens being around the outside. Connect them all with a single bond. And then don't forget to subtract 2 plus 2. Subtract 4 from your pool. So 18 minus 4 brings us down to 14 electrons. Now the next step is to give the outer guys an octet. Neither oxygen's happy because they only have 2 in the bond, so they need 6 more. So I'm going to subtract those 6. That's 8 electrons. And now I'm going to put 6 over here. And that means 8 minus 6 is 2 left. I have 2 left. So where do I put them? Well, you probably noticed that this guy looks good and this guy looks good. But poor little sulfur is only sharing 2 and 2. It's only got 4. So it needs some more. It actually needs 4 more, but we have a little dilemma here because we only have 2 left in the pool. Don't do this. Don't say, well, it needs 4. Let me throw 4 on, because you don't have 4. You only have 2. So only put one set, those 2 electrons on. Don't make up electrons out of thin air. Once your pool is empty, it's empty. There are no more. So here we move on to plan B. When you run out of electrons, you have to move on to plan B. This is why it's so important to keep track of electrons, so you know that it's time to move on to plan B. Now, what is plan B? It's very simple. This little sulfur in the middle says, I have 2, 2, 2. I have 6, but I need 2 more. It looks at the 2 oxygens and says, can somebody hook me up? Can somebody take one more set of electrons that they have around them and send them around me? Eeny, meeny, miny, mo, doesn't matter which one. Pick your favorite oxygen. Pick a set of electrons. Again, it doesn't matter which one. And cross it off. Or if you have a great eraser, erase it. Just be careful you don't erase it and leave faint little lines. So cross it off and do this. Make a double bond. And now, sulfur's got 2, 4, 6, 8. Oxygen still has 2, 4, 6, and 8. This isn't there anymore. Instead, it's been turned into a double bond. So we can just replace that with a nice looking bar here. So that's how you know whether or not to make double bonds. You keep track of your electrons and you realize, uh-oh, I'm short. My center atom's not happy and I don't have enough electrons. So that's where you go to plan B. And that's where you start making double bonds. Now, what does this guy look like in the real world? Well, you're going to count up the atoms that are bonded to the center atom. We have 1, 2 atoms bonded to the center. Now you look on your reference sheet. Here's your center atom. You have 2 options. You have something that looks like this. This is what we call linear because it's basically a straight line. And you have something that looks like this. And this is called bent. Now the reason bent is bent and not linear is because it's got 2 electrons right there. So does this drawing. We've got 2 electrons. So that's going to cause this molecule to bend. It's going to push down on these negative electron clouds and force them down and away. Remember the Vesper theory? It pushes down, it repels other negative regions. So let's take a look at what this would look like. So here we are with our models. Now this is our center atom, this purpley guy here. We have 1 regular oxygen and 1 double bonded oxygen. Now it really doesn't matter if you have the double bonded oxygen on this side or if you have it on this side, because it's basically the same molecule, just looking at one side versus the reverse side of it. You could have it up here, you could have the other one down there. What is going to change, though, is the fact that there are 2 more electrons sitting up at the top. And those electrons cause these guys to bend down. They repel. Now watch. Without it, with it. Without it, with it. So when you are deciding, is it linear, straight line, or is it bent, you're always looking for these electrons, and they should be on your drawing. And in our drawing, they're right there. So that causes the oxygens to bend down. So that's what you're looking for. That's a big difference between linear and bent.
So here we have SO3. Now sulfur is in group 6, so it has 6 valence electrons. Oxygen has 6, and there's 3 atoms of oxygen in 1 molecule of SO3. 3 times 6 is 18. So the sulfur and the oxygen say to each other, let's pool our electrons together. Let's put our 6 and 18 together and let's get 24 in the pool. And we're going to use those 24 to create a molecule, to make sure that everybody has the octet, that everybody's satisfied, but we have to divvy them up equally. So let's start with picking your central atom. Now there's only one S and there's 3 O's, so the S goes in the center. The next rule was to connect all of the other atoms to the central one using single bonds. So let's go ahead and do that. And remember, each bond is 2 electrons. So now we have to subtract the number of electrons we've used so far from our pool. You always have to keep track of your electrons because you want to see it go down to 0. So here's 2 here. 2 plus another 2 is 4, plus another 2 is 6. So 24 minus 6 leaves us with 18 electrons. Now the next rule is to give the extra electrons to your outer guys and give them an octet. So we have 18 electrons, and each one of these oxygens needs 6 to have the octet. It's got 2 in the bond, but it needs 6 more from somewhere. So it's going to take it out of the pool. Remember, they're going to divvy everything up so everybody has an octet. I'm going to show you why it's so important to keep track of your electrons. We just gave away 6 plus 6 plus 6. We just gave away 18 electrons. And our bank, our pool of electrons, is empty. It's down to 0. We're not done yet, because the sulfur in the middle doesn't have enough electrons. It only has 2, 4, 6. It's short 1 set of electrons. So what it's going to do, it's going to get another set of shared electrons from one of these oxygens. Eeny, meeny, miny, mo, pick your favorite oxygen. It doesn't really matter which one. And one of these sets, instead of just hanging around the oxygen, is going to turn into a double bond. So this is no longer going to be just around that oxygen. Instead, you can imagine it going here, going here, and turning into a double bond. And now those 2 electrons will zip back and forth between the sulfur and the oxygen. Now this oxygen did not lose its electrons. It still has all 8 electrons. It's got 2, 4, 6, 8. So this has 8, and now sulfur has 2 plus 2 plus 2 plus 2. So sulfur has all 8, and it has what we call here a double bond. And that's how you know whether or not to make a double bond. The fact that we ran out of electrons and we realized that the sulfur wasn't happy was an indication that we have to turn some of those extra electrons into a double bond. So you have to keep track of your electrons. Now notice what I did as I was talking. I took the electrons that were around the oxygen and I scooted them over a little bit. I changed the angle so they weren't at 90-degree angles, because according to the valence shell electron repulsion theory, these electrons don't like each other. They're all negative, so they repel. So these electrons want to get as far away from these electrons. Before, we had them sitting here, and they were pretty close to these guys. But if we move them away, so they're kind of on this third of the, I guess, of the drawing here, then they're away from these guys, and they're away from the electrons in the bonds. So we have 3 regions of electrons in this drawing. So you never want to force them together when they could spread out and be apart from each other. These guys, there's 4 regions. 1, 2, 3, 4. So they're as far apart from each other as they can be. Same thing over here. However, the whole molecule could be rearranged a little bit. When we're done with this, we're not going to have this oxygen, this oxygen, this oxygen kind of all squished on this bottom half of the molecule with nothing up here. That's not the right shape for it. So although this is correctly drawn on paper, we do need to consider what the real 3D shape would be. So let's go to our model. So here's our sulfur. Let's add oxygen, oxygen, oxygen. So there's our 3 oxygens. Now remember, this is when we realized that sulfur in the middle wasn't happy. So we ended up taking one of these single bonds and turning them into a double bond. And this changes the angle. So now, instead of having the sulfur in the middle and the oxygen, 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 we end up in the 3-dimensional shape having a third up here. One of the oxygens is up here, one of the oxygens is in this third, and the final oxygen is in this third. So they're all equidistant from each other. All of these electron clouds want to get as far away from each other as possible. And that's what SO3 would look like. All right, so let's try carbon dioxide. Let's tally up the electrons. We got carbon and oxygen. Carbon's got 4 because it's in group 4, or 14. Oxygen's got 6, and there's 2 of them. 6 times 2 is 12. That should be a times. So 4 plus 12 is going to be 16. There's 16 electrons that we're going to use here. Now pick your center atom. When in doubt, carbon makes an awesome center atom. Plus there's only one of them. So put your 2 oxygens here, connect them with a single bond, and then what do? And if you're thinking subtract 4 from 16, you're right on the money. Good. So you have 12 electrons left. Now watch this work out here. We're going to put 2, 4, 6 electrons there. 12 minus 6 goes down to 6. Uh-oh, we only have 6 electrons left, and a lot of unhappy atoms here. 2, 4, 6. Uh-oh, our pool is empty. And look at that center atom. Is carbon happy? It's got 2 and 2. Not happy right now. And we can't just fabricate electrons. We can't just make them up out of thin air. Our pool is empty. There's nothing left. So here's what we're going to do. Carbon's going to look at the oxygens and say, you guys all have your octet. I don't. Maybe you guys can hook me up. Maybe instead of just keeping them around you, you can share them with me. So this oxygen's nice. This oxygen says, sure, I'm not going to keep them. I'll let you borrow them for part of the time. And we'll make a double bond on this side. And the carbon says, great, but I'm not quite happy yet. I've got 2, 4, 6, I need 2 more. So then this carbon looks at that oxygen and says, well, what about you? Can you do the same thing? And this oxygen says, sure, I don't need to keep them around me permanently. I can send them back and forth around you too, so we can share them. As long as you don't keep them, as long as you share them with me, I have no problem donating 2 more and making another bond. So basically we have a double bond on one side, double bond on the other. Now, if you happen to draw this, if you were working this out on your own, and you ended up with a triple bond on one side and a single bond on the other, that's not wrong. That's fine. And actually, what this does in real life, sometimes it looks like that, sometimes it looks like what I just drew, and sometimes it looks like this. Remember, these electron clouds are basically just big fuzzy clouds, and the electrons can kind of go back and forth. So sometimes one side might be overloaded, sometimes they might be right in the middle, and then other times the other side might be overloaded. So don't feel bad if you drew triple bonds and you're looking at my drawing and it differs from what you did. But we can just draw it and try to focus on symmetry. Now, if we look at the shape of this, we have 1, 2 atoms bonded to the center guy. So that gives us 2 options. It can either be linear or it could be bent. And what we're looking at to differentiate between the two is those electrons on that center atom. There are no electrons on that carbon. So here's our center atom. We got a double bond on one side, double bond on the other. And that looks like it's a straight line, doesn't it? There's no electrons on that center atom. So it remains a straight line. It remains linear. So let's look at how CO, carbon monoxide, forms. Now carbon comes in with 4 valence electrons. Obviously it's not the octet, it's short 4, so it's not happy with the situation. And oxygen doesn't have an octet either. Oxygen's only got 6. So the 1C and the 1O look at each other and say, neither of us are happy. There are no metals to give us those electrons and make ions. So instead, let's pool our electrons together. Let's take our 10 electrons and divvy them up so that everybody's happy. So when you pick your central atom normally, it's going to be a carbon. In this case, there's only one carbon and one oxygen, so you really don't have a central atom. You just have a left and have a right. Now the first rule is to connect your central atom to the outer ones with a single bond. So we're just going to use one bond. That's 2 electrons, so that leaves us with 8. Now, the next rule is to give your outer guys an octet. Well, we really don't have an outer guy. We have a left and a right. Pick one. It doesn't matter which one. If you like carbon better, give carbon the octet. If you like oxygen better, give oxygen the octet. Let's go with carbon. We're going to give carbon the octet. It's got 2 already in the bond. Let's give it 6 more. Now our bank is going down. Our bank, or pool of electrons, there's 8. Now we're down 6, so that leaves us with 2. So there's 2 electrons left. Now you might be looking at the oxygen saying, well, oxygen needs a lot more than just 2. Now we're going to give it 2, and we're left with 0 electrons left. And we have a little bit of a problem, because although carbon's happy, oxygen is not. Oxygen doesn't have an octet, and in fact it's short 4 electrons. So the oxygen looks at the carbon and says, you have an octet, how about hooking me up with an octet? So 2 of those electrons are going to be turned into another bond. Carbon's not losing them, they're going back and forth. They'll come back to carbon, but carbon's also going to make the oxygen closer to the octet. And oxygen says, that's great, but I only have 2, 4, 6, I need 2 more. Carbon, do you want to do that again? So carbon makes 1 more bond. Those electrons are going to go back and forth. And this is what our structure is going to look like. A triple bond. So that's how we form triple bonds. And that's how we knew to form a triple bond, because the number of valence electrons went down to 0, and not everybody was happy. So we knew we had to start reshuffling some electrons. So we've got our triple bond here. We've got the unshared pair of electrons on the far side of carbon, and we've got another set of unshared electrons on the far side of oxygen. These 2 sets of electrons want to be as far away from each other as possible, so they're 180 degrees away from each other. So if you had them on the bottom or off to the side or whatever, just kind of rearrange them a little bit so that they're on the back sides and they're as far apart from each other as possible. Now this is an easy shape. You've got 2 atoms, so it's going to be linear. 1 here, 1 there. It doesn't matter which way you turn it, it's still going to be linear, even though there's a triple bond connecting them. So let's look at our model quickly. So here's our carbon, and there's our oxygen, and there's our triple bond between the 2. And again, any which way you turn this, it's always linear. 2 atoms always makes a straight line. 3, not always, but 2, always. So here we have 2 hydrogens, 1 carbon, 1 oxygen. There's not a single metal in sight. No one's going to donate electrons. Hydrogen, each one only has 1 electron. Carbon has 4, oxygen has 6. And they look at each other and they say, let's pool our valence electrons. Let's put all 12 of them in a little pool and we'll divvy them up so that everybody's happy. So the first thing you do after you pool your electrons is pick your central atom. Carbon usually is your central atom. So we'll put carbon here. Now you're going to surround carbon by the 2 hydrogens and the oxygen. So it doesn't really matter where you put them now. You'll see when we look at the shape, what shape it becomes. But for now, just kind of spread them out into the 4 corners, obviously leaving one of those corners blank. Next rule, connect your central atom with single bonds. Each one of those single bonds is 2 electrons, so keep track of that. 2, 4, 6. We are now down to 6 electrons left. So where do they go? Well, you go all around the outside of your molecule. You make everybody happy. Now this little hydrogen is okay just the way it is. It's already got 2 electrons in the bond. This hydrogen's in the same boat. It's got 2 electrons. This oxygen is going to take those 6 electrons out of the pool and make itself happy. So this oxygen is going to have its octet by taking those last 6 electrons. And now we're down to 0, and we have a problem. Take a look at your carbon. Is the carbon happy? Does it have an octet? It's got 2, 4, 6. It needs 2 more. So we're going to look at our bank first and realize we have no more electrons to give it. So we have to try another route to making the carbon happy. what we're going to do here is take a set from oxygen, because hydrogens have no more to give up. But oxygen has some. It's going to take these two and say to carbon, here, we'll share. They'll go back and forth between us. I'm not going to lose them, and you get to have them for part of the time. So we have 2, 4, 6, 8 around carbon. The carbon's happy, and oxygen's still happy. 2, 4, 6, 8. These guys, electrons, don't like each other, so they want to spread out a little bit. And they're going to break up this region into three parts. 1, 2, 3. So the three sections of negativeness. And if we look at this molecule, just like we had in an earlier problem, there's nothing up here, and there's a whole lot down here, all these electron clouds. So this really isn't the best shape for this. So let's look at a real 3D model. Remember, we have 2 hydrogens and a double bonded oxygen connected to the carbon. So here's our 2 hydrogens, and let's add our double bonded oxygen. And when we look at our structure, this is what we have. We have this entire 3D sphere divided into 3 regions, 1, 2, 3, and they're each equidistant apart. So it looks like a triangle, plus they're all on the same plane. I could draw one line through this and hit all of the atoms. This is trigonal planar.
All right, last 2 here. Let's do oxygen. This is oxygen gas, O2, and this is ozone. So we'll do oxygen gas and ozone. So O2. Each oxygen has 6, and there's 2 of them, so that's 12 electrons that these guys are going to divvy up and share. So, trick question. Which is your center element? It's a trick because there's only oxygens. So O-O. That's 2 electrons. Don't forget about subtracting those 2 electrons from your pool. So now our pool is down to 10 electrons. All right, so here's a little lesson. Don't try to make them both happy at the same time. Pick your favorite oxygen and make that guy happy. And then whatever's left over, you put on the other atom. And then you'll fix things by making doubles and triple bonds. But right now, eeny, meeny, miny, mo, I like the left guy. So I'm going to give the left guy 6 electrons. So 10 minus 6 is 4. I'm going to put the remaining 4 around this guy. And now my bank is 0, and I have a problem, because that guy's not happy. He's only got 2 in the bond, 4, 6. He needs 2 more down here, but there's none left in the bank. So now I move on to plan B. What's plan B? This little oxygen looks at that one and says, hey, hook me up, make some double bonds with me. So these 2 are no longer around this oxygen. Instead, they're a double bond. And that would be a linear molecule. It would be this, O2. And that's what oxygen looks like in the real world. So take a breath. The oxygen that you just inhaled, that's on its way into your lungs, then it's going to go into your bloodstream, then it's going to go into your cells. That oxygen is hooked up in pairs like this. It's a one molecule made up of 2 oxygens with a double bond in between. Now let's look at ozone. Hopefully you're not taking a breath and breathing in ozone because it's an irritant in your lungs, and it really bothers people with asthma. And it smells kind of funny after lightning storms. And we'll talk about why ozone forms later on. But here's ozone. It's a different molecule because there's 3 oxygen atoms. So you need to do 6 times 3 is 18. So now there's 18 electrons in the pool. And there's, again, 3 oxygens. Now, don't forget about your bonds right away. 2, 4, subtract 4. Remember, if you don't keep track of your electrons, you won't know if you ran out completely and have to make double bonds, or if you have any left that you can just throw on the center atom. So let's see how this plays out. Right now I'm down to 14 electrons. I'm going to pick my favorite oxygen, the outer guy, give him an octet. 1, 2, 3, 4, 5, 6, plus 2 in the bond. 14 minus 6 is 8. 1, 2, 3, 4, 5, 6. 8 minus 6 is 2. I have 2 electrons left. Now, how many do you think oxygen really wants? Is 2 going to cut it? And the answer is no. But we're going to take those 2 and we're going to use them. We'll put them up here. You can put them on the bottom if you want. Doesn't really matter. But our bank is empty. And we have a problem because this little oxygen's not happy. It's got 2, 4, 6. It needs one more set. So eeny, meeny, miny, mo looks at its favorite oxygen and says, I like you better. Can you hook me up?
And this guy says, sure, we'll make a double bond. Now, you have to figure out what shape this is. This guy that we drew first, this was linear. This is not linear because of those guys. Remember, you have two options whenever you have 1, 2 atoms bonded to the center. It could be in a straight line, it could be linear, or you could have them bent down like this. And the reason they bend down is because those electrons push them down. So let's take a look at the model. Remember, we had a double bond on this side and a single bond on that side? This is linear, but it also had 2 electrons up at the top, and boom, there you go. It bends down.